What if you could take a material so tiny that a pinch of it has the surface area of an entire soccer field? Better yet, what if it could also store hydrogen, store carbon dioxide, and even harvest water from the air? Honestly, you'd probably believe it's something straight out of Cooper Station from Interstellar, but it's actually the reality of metal organic frameworks, known as MOFs for short. In 2025, just a few weeks ago, this type of material won the Nobel Prize in Chemistry and catapulted Susumu Kitagawa, Richard Robson, and Omar Yagi into scientific history. Now, what exactly are MOFs? Imagine pouring out a box of Legos. You've got two kinds of pieces. Solid connectors, in this case being clusters of inorganic metal material, and rods that bridge between these links, in this case being called organic linkers, as academics define them. Click them together, and instead of ABS plastic, you've built a molecular framework full of open windows and passageways. In essence, they're molecular Legos, where each one of the openings you create by linking your inorganic compounds with your organic ones creates a space of perceptually infinite possibilities. Moving on. Much like we can design our own Lego pieces to be whatever we want them to be, we can swap out the metals and organic compounds that make up MOFs to target specific molecules. The possibilities are far too long to enumerate, so we'll be focusing on the most pertinent three: gas storage, carbon capture, and water harvesting, and why the Nobel Committee really took notice of them. Now, fair warning, MOFs being the victors of the 2025 Nobel Prize has stirred up some controversy in the chemistry community, mainly because it hasn't been put into large-scale practice yet. So, it'll be really exciting to see how their development will pan out in the future, and if they will be protagonists for years to come. Now, why did I specifically mention hydrogen, and now may I add methane? Typically, storing enough hydrogen or natural gas where its main component is methane for fuel purposes is like trying to fit a balloon into a small box. They're both bulky and very hard to compress gases. However, MOFs offer a clever solution to this little dilemma with their large surface area. They sort of pack these molecules into the tiny pores within their structure, effectively using every square meter of themselves to hold gas. In this situation, our Lego constructions turn into high-rise parking garages for hydrogen and methane, allowing far more to be stored than if they were just traditionally squeezed into a tank or through pipes like we mainly do today. In fact, some MOFs actually have an internal surface area of up to 10,000 meters squared per gram, which is nearly 2 football fields in area, crammed into the size of just a sugar cube. But why exactly hydrogen and methane, though? And how can they work specifically with MOFs in the future? Well, as you may or may not know, hydrogen is a clean fuel, but its low density means that as a gas, it requires high pressure or cryogenic liquids for storage in significant amounts. Thus, even though it has the potential to transform our current scope of energetics today, our current technology doesn't make it very feasible to use at a larger scale. Fortunately, though, researchers have actually identified MOF materials that can surpass previous traditional hydrogen storage records. One famous early MOF, literally called MOF-5, and as you will see, the metal organic frameworks throughout this video are going to be referred to as MOF-5, or a series of elements, dash a number. But I digress. This MOF-5 demonstrated extraordinary stability and pore volume, proving that these materials can actually work as adsorbents that hold substantial amounts of hydrogen when cooled with, unfortunately, liquid nitrogen. For now, it looks like the cryogenic cooling aspect of both of these gases will have to stay until something is reinvented in the cycle. The vision here, however, is that any hydrogen-powered cars in the future will have MOF-filled tanks instead of the current heavy, high-pressure cylinders that we use right now. The potential in foresight is humongous. An MOF tank could improve safety and potentially reduce costs tenfold because it functions at lower pressures. Methane, on the other hand, is a little bit more complex to deal with. As I said before, it's the main component of natural gas. Storing it typically means compressing a tank to about 250 bar, which is extremely energy intensive and raises a lot of safety concerns. primarily causing incidents such as what happened at Chevron's Los Angeles El Segundo refinery a couple of weeks back at the time of this recording. MOFs enable this thing called adsorbed natural gas technology, ANG technology. Methane is adsorbed into a porous material so that you can store it adequately at much lower pressures, at around 35 to 65 bar compared to that 250 bar benchmark that I was talking about earlier. Now, I just want to be clear. I am referring to adsorption, and adsorption differs from absorption in that the former involves molecules clinging to a surface rather than drawing into a material like you'd find water being absorbed into a sponge. But I digress. This small detail of pressure and lighter tanks could extend driving range for natural gas cars. And yes, people actually use methane to power their vehicles. They gather natural gas from the ground and they pump it into their cars. It's actually very interesting. In fact, a densified MOF called HCUST-1, also known as MOF-199, achieved a record methane storage capacity of about 259 cubic centimeters at STP of gas per cubic centimeter of MOF. That's a lot. Even better, some more advanced MOFs like FE-BDP have built-in thermal management, releasing about 40% less heat when filling with gas compared to earlier iterations. But why is heat important? Well, when gas sticks to a surface, it releases heat. It's an exothermic process. It decreases entropy. So if your MOF tank gets too hot, it won't fill as efficiently. And as such, a cooler, more heat-tolerant MOF means faster, safer refueling and more widespread use of natural gas cars. However, there are some limitations. Despite the promise, gas storage MOFs aren't a magic bullet yet. One very prominent challenge is that they mainly grab gases by relatively weak forces linked to physical adsorption. They're fine at low temperatures or high pressures, but at room temperature, ultralight hydrogen in particular doesn't stick firmly. For any sort of practical hydrogen car, MOF tanks might still need to be cooled to cryogenic temperatures, like I said before, to reach even a fraction of their desired capabilities, which adds another layer of complexity that, say, traditional fuel sources like gasoline don't really have attached to them. With methane, MOF-based tanks work well near room temperature, but the MOF itself actually takes up space and adds weight. So the overall system still has to be optimized to beat a traditional gas tank, again, making things more convoluted than they have to be. Researchers, however, are addressing this by shaping MOFs into little compact pellets or monoliths and finding those with the best trade-off between gravimetric and volumetric capacity, which is basically lightweight versus space-efficient capacities. Another practical concern, though, durability. Actual natural gas isn't pure methane, but instead it contains impurities mainly in the form of water or other heavier hydrocarbons, which can degrade MOFs over time. For example, these extra components can actually occupy some of the MOF's active sites, sort of like a protein, cutting the amount of deliverable energy available by up to 50% if they're not dealt with accordingly. Now that we've seen MOFs as high-capacity gas sponges, let's look at how they can act as filters for a different type of gas, carbon dioxide. Moving on, though, let's talk about carbon capture and storage technology with MOFs. What I would say is one of the most significant challenges in our world today is the greenhouse effect, where we can find excess carbon dioxide in the atmosphere, which drives this greenhouse effect due to its IRA-active structure that allows it to redirect thermal energy back into the atmosphere through vibrations. With MOFs, we can actually snag these molecules directly out of a stream of mixed gases, like our atmosphere, like a sieve catching gold nuggets out of sand. That's pretty cool. And I would say they're rising to, this specific challenge as tailor-made CO2 sorbents, very specific and very individualized for this sort of issue. But that's not important. Thanks to the modifications that we can actually do in MOFs, they can be designed to preferentially capture this gas while letting go of other necessary ones like nitrogen or oxygen, and letting them pass through directly. Related to this, we can actually decorate the inside of MOF pores with chemical groups that bind to carbon dioxide through either physical attraction or even mild chemical reactions. Some MOFs, in fact, have open metal clusters that act like magnetic hooks for CO2 molecules, while other variations have little amine groups dangling inside of the pores that can chemically bind to CO2 in a reversible reaction. The big picture here is that we can actually use these MOF-based filters to capture carbon dioxide from direct industrial emissions before they hit the air. And they're actually pretty accurate if you look into it. Certain MOFs are so effective that they can pull out carbon dioxide out of ultra-dilute air with a concentration of about 0.04% CO2, basically making MOFs artificial trees. When talking about this, one benchmark that's commonly cited when we talk about this sort of application is Mg-MOF-74, which has a surface area of about 1,600 meters squared per gram and can hold about 1 millimole of CO2 per gram at room temperature. Now, if you're wondering about any lab experiments that actually prove these claims, we can look at some of Omar Yagi's MOFs, which have been shown to capture CO2 from power plant flue gas, being the mixture of gases that are released when a fuel is combusted before it escapes into the air. Instead of corrosive liquid amine solutions, the current industry standard for CO2 capture, an MOF can do the same job as a solid that's easier to handle and transport. Even then, because of their tunability, like I talked about before, we can adjust them to work at different CO2 concentrations or humidities, allowing us to retrofit these MOF capture systems to practically any environmental condition worldwide. But what I find most exciting is that these MOFs might overcome some of the drawbacks of current CO2 capture technology. Liquid amine scrubbers, the current industry standard that I talked about before, for instance, are effective but very energy intensive, and they can cause toxic byproducts, apart from suffering from degradation over time. MOFs, by contrast, don't evaporate or decompose the way these liquids do, and they can also be potentially regenerated through the previously mentioned reversible reactions. This can be done through clever methods like pressure or temperature swing specifically. In one study, a zirconium-based MOF called UIO-66, modified with OH groups, was both water stable and captured more CO2 than a benchmark MEA amine solution on a per gram basis. This result hints that MOFs could go beyond simplifying CO2 capture setups and, improve the capture of CO2 worldwide when we're talking about areas like China or India or certain parts of the United States that are very heavily polluted due to industrial needs. And as the population will inevitably grow, this MOF solution could become even more pertinent. However, that being said, MOFs for this carbon capture and storage system technology are not plug and play ready at a massive scale yet. There are many noteworthy challenges to address, just like the gas storage applications we talked about earlier. One main issue, similar to the gas storage, is stability. Flue gas and air both contain moisture, oxygen, and other contaminants. And many early MOFs would break down if you so much as breathed on them. Okay, maybe I'm exaggerating, but they weren't very water stable, so they can't really go head to head with the sort of moisture that you find in the typical atmosphere. Modern MOFs, like those built on stable nodes or zirconium or aluminum clusters, have improved this deficit though, with some being able to withstand humid conditions and many cycles of CO2 capture and release, ensuring a little bit more of a long-term plan for durability. However, it is an ongoing effort and it's yet to be fully realized, much like most applications of MOFs. Another roadblock is the energy needed to regenerate these metal-organic frameworks. Even though they're very efficient, you still have to spend a lot of energy to get that CO2 back off the sorbent, usually done by heating or vacuuming. If an MOF holds on to carbon dioxide too tightly, it might grab a lot, but then require high heat to regenerate. Not ideal. If it holds too weakly, it might not capture enough in the first place. So, as you can see, there's a little bit of a Goldilocks problem here. Much like the gas storage capabilities of MOFs, CCS needs thermal management. It's very essential. MOFs are typically poor thermal conductors. MOF-5, like the one I mentioned before, has a thermal conductivity of about only 0.3 watts per meter Kelvin, which is nearly comparable to an insulator. This downside means that when CO2 binds and heat is released, that heat doesn't spread out quickly. Similarly, when we heat the MOF to regenerate it, parts of it can stay cool. However, though, there's another issue. We can make MOFs by the gram or kilogram in the lab, but capturing carbon dioxide at a million-ton scale would require producing these MOFs by the ton, cheaply and consistently at that. It's a very big issue, specifically dealing with the sort of materials or the environment or the geographic location where you might want to develop these MOFs. However, active research is looking at low-cost synthesis and even using bio-derived linkers or simpler ingredients for more sustainable practice. Finally, while MOFs avoid the toxicity of amine liquids, they're not entirely off the hook. Some contain heavy metals or use solvents in production. So the sustainability of the MOF itself is a factor to keep under consideration if we really want to expand them on a global scale. Now, we talked about clean energy and clean air, but what about one of the most important things in the world, clean water? Picture yourself in the desert with bone-dry air and no water source in sight. Now imagine a magic little box that fills a glass of water for you overnight from just desert air, powered only by sunlight. That's essentially what researchers have built using MOFs, devices that harvest water out of thin air. Our atmosphere always contains some sort of moisture in the form of water vapor, even in very arid climates. The challenge is, though, grabbing that vapor when it's extremely scant. When I say scant, think of humidity levels less than 20%, which are very common in deserts. Traditional dehumidifiers or fog nets don't work at such low humidity levels or need lots of energy to work at those levels. But certain MOFs act like super sponges for this very scarce water. They can capture H2O molecules at night when the air is a little bit cooler and more humid, and then release the water as liquid when heated by the morning sun. But how exactly does it work? A great example of this is an MOF called MOF-303, an aluminum-based framework that starts soaking up water at about 10 to 15% relative humidity. In desert night conditions, humidity can rise upwards to 30% as temperatures drop. Some of the MOF's pores, which are lined with sites that attract water, become coated with these water molecules. When sunlight hits this device, it warms the MOF up, and because MOF-303 has its affinity drop as temperature rises, it releases the water vapor into a condenser. In an August 2022 field test in Death Valley, one of the driest, hottest places on Earth, a passive MOF harvester using this MOF-303 was able to produce about 0.2 liters of water per kilogram of MOF per day, 114 to about 210 grams per kilogram to be precise, just from ambient air, with no power other than sunlight. To put that into perspective, if you had about 5 kilograms of MOF, which would fit in a device about the size of a microwave oven, you could collect roughly a liter of water a day in desert conditions. In more moderate climates, or with higher humidity at night, yields would be even higher. This atmospheric water harvesting with MOFs could be completely transformative for water-scarce regions anywhere around the world. Think of remote villages from rivers and lakes, or military troops in the field, or even future Mars colonies. A compact MOF could provide a reliable daily water supply without needing any sort of electrical grid. Atmospheric water harvesting with these MOFs could completely change the scope of, any sort of resource wars that may arise, specifically with the rising global climate that these MOFs actually address as well, like I said before. It also gives the function to decentralize water access Instead of massive infrastructure like dams or pipelines regulating water, each home or community could have a little off-grid water source for themselves. As impressive as it sounds, though, MOF water harvesters won't be replacing your city's water utility for now. One vital limitation here is the scale. The yields, while improving, are modest in absolute terms. A few liters per day can sustain an individual or little small family's drinking needs, but supplying a whole town would require either a lot of devices or many of them working in parallel. As I said before, these materials that make up MOFs, MOF-303 or any of the other ones I talked about before, they aren't cheap, yet, at a large scale. Durability is another issue, like the other two applications. As MOFs cycle through absorbing and deabsorbing water daily, they can undergo stress. Another challenge is that truly extreme deserts with relative humidity levels less than 10%, even at night, push the limits of what these MOFs are capable of doing. Since they might not collect much if the humidity never rises past that 10 to 50% threshold that they need. With this, we can also call into question the purity of this generated water. Water from an MOF will be distilled quality, but we must ensure that no trace of MOF, linker, or any byproducts for that matter leach into the water. So far, though, designs have the water condense on a separate surface, so the MOF itself doesn't touch the liquid we drink. However, as we advance this technology, we may have to introduce potentially toxic materials to help the efficiency and production of the water that we need. From fueling the future with clean hydrogen, to filtering out excess CO2 warming our planet, to quenching thirst by drawing water from desert skies. MOFs exemplify how innovative chemistry can tackle such a wide array of global challenges, which are surprisingly interlinked. It's really no wonder that the Nobel Prize Committee described them as creating previously unforeseen opportunities. Even with what I discuss in this video, I've barely even scratched the surface of what's possible with these magnificent devices. There are tens of thousands of MOFs known, and researchers are exploring them for catalyzing reactions, drug delivery, further pollutant removal, energy storage, and more. However, for now, there are numerous limitations that are holding back certain aspects of MOFs. So it's not surprising that they haven't been implemented on a large scale and received some heavy criticism this year. Yet, as we look to a future of climate action and resource stewardship with greener chemistry, MOFs are stepping onto center stage as microscopic heroes of material science, ready to store, capture, and release molecules on command. In a nutshell, MOFs give us molecular Legos to build a cleaner, greener world, and this is just the beginning of what we can do with them. Thank you to everybody watching for tuning into my first episode of Chemistry Podcasts. I swear the quality will be getting better and better from here on out, and I'll be discussing maybe cooler topics that aren't so academically based, like the chemistry behind F1 cars, their engines, their tires. That's something that I'm looking into because I'm very interested in F1 and I think that'd be pretty cool to talk about. So, I digress. Thank you for watching, and hopefully you come back to watch more.